Okay, so I have a few different bits and pieces that I thought would be useful to cover. Starting with this, which is a simple observation that bottom pressure variability is much less than sea level variability, especially once you start looking at relatively long timescales. So this is a model result showing how interannual variability in bottom pressure is down at the millimeters level. And it's very variable. Different places show different things. So just as Rui was saying, we have this intrinsic variability versus forced variability. Sometimes the intrinsic variability can be much higher. It depends where you are. If you're in the tropics, things tend to be suppressed. And all of these things you can make sense of. There are good dynamical reasons why you see these patterns. So this is the background to a study I was involved in about, well, getting over a decade ago now, where we realized actually that the smallness of the bottom pressure variability could be used as an advantage, given that it's dynamics that we're normally looking at as oceanographers. If there's no dynamics, then maybe what we're seeing is something else. So we try to actually weigh the oceans and look at the total mass of the ocean. And I thought this was worth showing a few results from, just because of the process of putting together the different signals that go into measurements. So these are two of the DART buoys from the Pacific, and the time series from those two places. There we go. So the red line at the top here is the time series from the bottom pressure recorders after a detrending has been done. So there are multiple deployments here. Each of these little ticks is a new deployment with a new detrending. The black is the sum of all of these other causes. So whereas an oceanographer would tend to look to this line, the ocean model, as what you expect to see, there are lots of things that are missed out in an ocean model. First of all, there's the total mass of the ocean coming and going as the ice melts and refreezes. That's the main cause of it. So exchange of water between ocean and solid earth. There's long period tides. So this curve here is mainly annual, semi-annual, but also the pole tide turned out to be quite significant. And this curve at the bottom, that's the atmospheric pressure averaged over the entire ocean. So that's the part of the atmospheric pressure that can't be compensated in an inverse barometer way. The ocean can't get out of the way because it's the whole ocean. And I find it very interesting to see how comparable the sizes of all of these signals were in adding up to the total that you see at one particular spot. So those were in this quiet region in the tropical Pacific. This is a different ocean model, and we've got 54 years worth of data here, 5-day averages, and it's just the standard deviation, all of that, with the seasonal cycle and a long-term trend removed. Again, very different kinds of variability in different places. So a lot of this high variability on the shelf is saturated deliberately so that you can see the smaller values elsewhere. Lots of variability up on the shelf is dominantly wind driven and to some extent pressure driven and quite deterministic. And a patch like this, which is on the abyssal seafloor at the foot of the continental slope, tends to be dominated by mesoscale variability, which is completely stochastic, internally generated nonlinear variability. Some places around the Southern Ocean, there's a combination of the two. So some of these large scale patches can actually be very deterministic in their large scales, but then there are small scale variability on top of that. But all you're seeing is the amplitude here, not the length scale, which will be dominated by the mesoscale variability. But the thing I really want to focus on here is, you see this strip between the high variability on the shelf and the high variability in the abyss of very low variability. We're down at a couple of centimeters along the continental slope region, and all down the eastern boundary as well. Very low variability on the continental slope. That's because waves on the continental slope propagate much faster than they do in the ocean interior, which means that they're much less likely to become nonlinear. And the behavior of the dynamics on this continental slope region is really quite different from most parts of the ocean. And that's very exciting from the point of view of monitoring what the ocean's doing. If we take that entire strip around the globe, so again, we're still on a model result here. This is 12th of a degree ocean model, and it's the time mean bottom pressure over 54 years as a function of distance along the continental slope and depth.
So 1,500 meters.
So 150,000 kilometers we have, or 160,000 kilometers of continental slope we have all the way around. And you can see how amazingly coherent these pressure patterns are. So I've subtracted off a reference function of depth based on what you see, what's happening in the Eastern Atlantic. As a result, nothing is left in the Eastern Atlantic. So that tells you how coherent the bottom pressure was all along the eastern boundary of the Atlantic. That's all of this region.
1 minute.
So huge coherence. And this is actually dominated by the meridional overturning circulation. This pattern, which you see on the western side of the Atlantic, is the pattern of pressures associated with a northward flow in shallow water and a southward flow in deep water. And it's also there, if you look at the long-term trend, the same pattern. So there's in this model, a decline in the MOC over those timescales. So we can actually, within the model, measure the MOC very nicely just from pressures, the difference between pressure on the eastern and the western boundary on these regions. We're capturing more than 90% of the variability. I don't know what's happened to you. There you go. I'll skip that one. We've tried to measure this. So this is an experiment with bottom pressure recorders down the continental slope off Nova Scotia. We have these 6 instruments, and because we suffer from the usual problem with drift, we try to do it 2 ways. So we have bottom pressure, but we also have density and current measurements. The current tells you the pressure gradient horizontally, and the density tells you the vertical pressure gradient. So you should be able to get the difference in pressure between 2 sites from these density and current measurements, as well as you can do it from the BPRs. And I think this is really quite nice because it works. This is 1 to 50 day bandpass filtered results. And the black line is inferred from current and density. The gray line is the straight difference from the BPRs. And you're seeing the standard deviation of the difference here. So this is going from the top one to the next one, the top one to the third one, top one to the fourth, top one to the fifth. The 6th one was down on the abyssal plain and was doing rather different things. we're getting sub-centimeter agreements on all of these timescales. So it really is possible to beat down that noise, whatever its source, whether it's stochastic or deterministic, by separating out the dynamic part from the non-dynamic part. Now, any vertical shift in the land, of course, won't show up in the dynamics. So it would be in the BPRs, but not in the other way of measuring things. That's what's left in the BPR measurement after we subtract out everything else. So it's the drift. And if you fit your exponential plus linear and remove that, then this is what remains. So that's the kind of level that you can hope to find for a tidied up signal if we use BPRs plus these ancillary measurements as a way of extracting out the ocean dynamics. We've also looked at the absolute bottom pressure, doing it from a tall mooring. If you measure sea level and density, you can infer the bottom pressure. That's really tricky. You can get to maybe a couple of centimeters accuracy for 1 year means. You need really careful calibration and a lot of ship time, a lot of work goes into that. So I'll finish there just to say that bottom pressure is incredibly valuable for large scale ocean dynamics because of this wonderful filtering effect of the continental slope, where we get to see the large scales. But we can also do this thing where we look at the differences down the slope, and we can get those differences to sub-centimeter accuracy with the two independent routes. So we can actually infer the vertical land motion as well as the ocean dynamics. Okay, I'll stop there.